Okay, so we are at the outer edge of the solar system today. We want to talk about Pluto and Charon and probably also the Kuiper Belt today. And then we'll be done with the solar system's big objects. Next week, we can talk about comets and asteroids and smaller objects. And then we'll probably spend a day talking about the formation of the solar system. And then we'll move on to some other stuff. So this picture is the best picture we had of Pluto and Charon up until about 2014 or so. They are very far away. They're very dim. We didn't even know Pluto existed until the 1930s. Pluto's moon Charon wasn't discovered until I think the mid 1980s. It wasn't in the textbooks when I was a kid. So we knew very little about Pluto and Charon until very, very recently. These are not photographs, but actually maps that were made of Pluto and Charon, I think using the Hubble Space Telescope, just looking at how they vary in brightness as they rotate and making some guesses about where the brighter versus darker regions are on the surface. So not exactly a photograph. We knew they had surface detail, but we didn't really know much about them at all. Here's another sort of brightness image of Pluto based on just making some guesses about its features on looking at how its brightness changes over time. We didn't really know much about Pluto and Charon in detail until 2015 was the year that the New Horizons spacecraft flew past the Pluto system. It was the first mission designed specifically to fly by Pluto and Charon. It didn't stop and orbit them. It kept on going out into the outer reaches of the solar system. So we got pictures of it as it flew by and then it was gone. So we have a handful of pictures of Pluto and Charon, not the detail that we have of, say, Jupiter and Saturn, where we've actually had orbiters orbiting those planets for years at a time. Just a few snapshots as we zip by. So here is Pluto, here's its moon Charon. One of the first things to notice about them is that Charon is really big compared to Pluto for a moon. Sometimes astronomers refer to Pluto as a sort of double planet system, even though we don't call Pluto a planet anymore, because the masses of the two objects are quite comparable. Usually when we think of a planet orbiting moon, we think of the planet as being stationary and the moon going around it in an elliptical orbit, because even though the moon pulls on the planet is so massive that it doesn't move very much. And we know that that's actually not true. For example, as the moon orbits the Earth actually moves in a little orbit of its own, but that circle that it moves in is entirely inside the Earth. That's not the case for Pluto. Pluto actually moves in a little circle of its own outside of Pluto as Charon orbits Pluto, and the center of mass of the Pluto-Charon system would be the point about which the two orbit. I think I said this when I was talking about the Earth and the Moon. If you want to imagine where that point in space is, you imagine taking Pluto and Charon and putting them on a big seesaw, and the point at which that seesaw would balance is the point that they both orbit around, the center of mass of the system. The fancy word for it is the barycenter, B-A-R-Y. This means it's a fancy Latin way of saying center of mass. The other interesting thing about Pluto and Charon is the way our moon is tidally locked to us. One face of the moon always faces us because of the tidal forces that have gradually slowed down the moon's rotation. Pluto and Charon are tidally locked to one another. That means that the month of Charon, the amount of time it takes Charon to go around Pluto once, is the same as the rate of rotation of Pluto and the same as the rate of rotation of Charon. So there's one face of Charon that always faces Pluto, and there's one face of Pluto that always faces Charon. If you lived on the other side of Pluto, you would never know that Charon exists. It would never appear in your sky. It's always the same point in the sky on one hemisphere of Pluto, because the month and the day are the same length. It goes around Pluto in the same time it takes Pluto to spin around once. And this is, again, due to tidal forces gradually slowing down the orbits and locking their rates of rotation. And because they are both so similar in mass, this locking is complete. Whereas for the Earth and Moon, the locking is only partial, right? The moon is locked to the Earth, but the Earth isn't locked to the moon. If the Earth-Moon system continued to orbit for another 50 billion years, eventually the Earth-Moon system would wind up same way, but the moon is much lighter, so it takes longer for that to happen. Here is a very nice picture of Pluto taken from the New Horizons spacecraft. Compared to the detail that we had before 2015 or so, we can see a huge amount of detail in this photograph. We see some craters, but not very deep craters, not very many craters, which suggests, again, anytime we see little evidence of craters, it means there's probably some kind of dynamic process that's covering up the craters. And we see really, really different terrain. We see this kind of rough, dark terrain, and we see this much smoother, lighter terrain. I think astronomers were probably a little bit surprised to find the terrain of Pluto as complicated as it was, but they had another object to compare it to, which is Neptune's moon Triton, which we talked about last time. In fact, if we look at Pluto and Triton side by side, they look really, really similar. There are rough, rocky regions of terrain, and there are smoother, icy regions of terrain. And there's some evidence that that terrain is dynamic, that it changes over time. Here's a more oblique angle looking over Pluto, and you can see the real difference between this kind of rough, rocky, mountainous terrain and this smoother, icy, more glacial terrain on the other side of the planet. And you can see places where the rocky terrain kind of pokes through the icy terrain. Pluto has mountains that are taller than these flat icy plains, and we can see the mountains kind of poking up through the ice here on the surface. Again, we see craters. There's a crater, there's a crater, there's a crater, there's a crater. But we also see evidence, like here, for example, that there's a crater that's being sort of filled in by ice, so gradually erased over time by the motion of these glaciers. We see places on the surface where the ice has shapes that don't look too terribly different from sand dunes on the Earth. They have this kind of rolling texture that we associate with what happens to sand on the Earth when it's subject to wind. That would mean that there would have to be wind on Pluto, which means there would have to be an atmosphere on Pluto. We'll talk about that in a minute. There's not exactly an atmosphere on Pluto, but there's something like an atmosphere surrounding the planet. And we can see what looks like evidence of flow of these great glaciers, this slow flow of this ice. This is not water ice, by the way. Remember, we are out at the very edge of the solar system where the temperatures are around 400 degrees below zero Fahrenheit. This is nitrogen ice, frozen nitrogen. The stuff that our air is mostly made out of is the stuff that the glaciers on Pluto is mostly made out of. And we can see what looks like this ice kind of flowing across the surface and covering up this more rugged, rocky terrain where the craters are up here in the corner. So there's some evidence that this nitrogen ice can melt and flow across the surface, giving Pluto an interesting dynamic geology, which we didn't really, geology isn't even the right word. Right, geo means earth. When we talk about the mountains and rivers and stuff on Earth, we call that geology. Interesting plutology, I don't know what to call it. Interesting planetary surface dynamics is, I guess, what we would call it. This is a picture taken by New Horizons, again, backlit, so looking back towards the sun. So we're looking at Pluto, looking at its dark side. And if Pluto had no atmosphere, that edge would be crisp. It would be just a perfect line. This blur is due to the fact that there is stuff in orbit or gravitationally bound to, orbit's not the right word, gravitationally bound to the surface of Pluto. What this is a very, very tenuous atmosphere. In fact, it's so tenuous, we don't even call it an atmosphere. We call it an exosphere. I think we may have used this word when we talked about Mercury as well. The atmospheric pressure would be less than 1/100,000th of Earth's atmospheric pressure. So this is an atmosphere that's barely there at all. But there are nitrogen molecules, there are methane molecules, there are carbon monoxide molecules and things like that, trapped by Pluto's gravity and constantly moving around the planet's surface. So while there wouldn't be probably wind that you could feel because the density is 1/100,000th of the density of the air on Earth, there are processes that slowly over time could perform the equivalent of wind erosion like we see on the Earth. It would just take 100,000 times longer because the density of the quote unquote air, the exosphere, is 100,000 times less. Here is Pluto's moon Charon, its biggest moon Charon. We see some features that are similar to places like Jupiter's moon Ganymede. We see this kind of cracked terrain, more craters, okay? So not as much dynamic surface processes covering up those craters over time. We do also see this orangey brown color that we've been seeing a lot in the outer solar system, this possible evidence of these tholins, these simple organic molecules that result from ultraviolet light driving chemical reactions involving carbon dioxide and methane and simple carbon molecules to combine together into bigger carbon molecules. You also see that Charon is visibly not quite round. If you look at the edge here, it's bumpy. It's not exactly a sphere. And that's because Charon is not quite big enough for gravity to squish all of its material into a perfect sphere. So Charon's right on the border between round enough or big enough to be round and small and irregular shaped. This raises the question about Pluto's demotion from planet to something else and what the reasons for that are and what the criteria are, which maybe we'll wait just a minute to talk about that until we get out in the Kuiper Belt. We'll talk about that. Pluto has some other moons. They're very small. And so this thing not quite fitting on the screen is Charon here. This key here is 10 miles. So Styx and Kerberos are less than 10 miles across. Nix and Hydra are like 30 miles on their longest dimension from one end to another. Again, small and irregular. Gravity definitely can't squish a 10-mile rock into a perfect sphere. And we didn't even really know about Styx and Hydra until we flew the New Horizons spacecraft past Pluto back in 2015 or so. Why is there a blank slide here? So let's talk about the edge of the solar system and this question of how to regard Pluto's place in the solar system at large. We have talked about the fact that Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune is not necessarily the edge of the solar system, that there is other stuff orbiting the sun outside of the orbits of Neptune and Pluto. We call this region the Kuiper Belt. We call the region outside that the Oort cloud. And there's all kinds of stuff orbiting the sun out there, from debris the size of grains of sand and snowflakes to objects the size of gravel and snowballs to objects the size of Pluto. And in fact, we think Pluto is the innermost Kuiper Belt object. The diameter of the Kuiper Belt is 50 AU. So we're talking about a size 50 times bigger than the orbit of the Earth. And then the Oort cloud could extend tens of thousands of AU beyond that. The Oort cloud would be a more symmetrical, spherical cloud of this very, very tiny debris. And the Kuiper Belt is more like a kind of donut-shaped orbiting ring of objects in closer to the sun. I think the Oort cloud is still hypothetical in that we don't have direct observational evidence that it exists, but the circumstantial evidence that it exists and the fact that it fits in with our pictures of how the solar system formed, which we'll talk about next week, is pretty strong evidence that the Oort cloud is out there. The Kuiper Belt, we know, is out there because we keep finding stuff out in the region of the solar system beyond the orbit of Pluto. For example, in 2003, we discovered a large object that we named UB313. It was called Xena for about 6 months, and they finally chose the name Eris for it. This is a painting. This is not a photograph or a picture of this object. We don't really know what it looks like because it's even further away than Pluto. And what we refer to these large, bigger than comets but smaller than planet objects out beyond the orbit of Neptune are Trans-Neptunian Objects, which is just a lot of words to say something out there beyond the orbit of Neptune. But the interesting thing about Eris is that it's bigger than Pluto. It seems to be about 1.5 times larger than Pluto. It is 97 AU from the sun, so quite a bit further away from the sun than Neptune and Pluto, which I think are between 30 and 40 AU from the sun maximum. And the question is, what do we call this thing Eris? If it's bigger than Pluto, and Pluto's a planet, then we got to call it a planet, which means that we have to change all the textbooks to say that the planets are Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto, and Eris. It even has a moon of its own. Eris has a moon, just like Pluto has a moon. So if we call Pluto a planet, there's no reason not to call Eris a planet. Well, then a few years later, we discovered an object called Sedna, which is about the size of Pluto, maybe a little bit smaller. And then a few years later, we discovered this object called Quaoar, which is about 2/3 the size of Pluto, but beyond Neptune's orbit. It reached a situation where if we grant Pluto the status of planet, then we should also grant Sedna and Eris and Quaoar and Haumea and Makemake and all these other trans-Neptunian objects the status of planet. Well, if we do that, then we have to accept the fact that there will be probably 50, 60 planets in the solar system. Instead, what we did was we changed the criteria for what counts as a planet. And by this new criteria, Pluto is no longer a planet. Pluto is a dwarf planet, or Pluto is a trans-Neptunian object, or Pluto is a Kuiper Belt object. So the new criteria for what's a planet and what's not a planet is entirely arbitrary. It's just a word that we can associate with anything we want. If we wanted, we could call the moon and Ganymede and Titan and Triton. We could call those planets too. They're big and they're round and they're places we could land and walk around on. Why aren't they planets? Just because they orbit something else? If I took the moon out of its orbit around the Earth and just plopped it down between Mars and Jupiter, we'd call it a planet. So the definition of what's a planet and what's not a planet is arbitrary. One of the things that was peculiar about Pluto from the beginning was that it doesn't seem to be made of rock like the terrestrial planets, like Mercury, Venus, Earth, and Mars. It seems to be largely made of ice, or at least a mixture of ice and rock. So that was one of the reasons that Pluto was considered unusual from the start. But there's so much stuff in the outer solar system that we have decided to call these objects that orbit in the Kuiper Belt or near the Kuiper Belt dwarf planets or trans-Neptunian objects. Here's a more recent account of them. In addition to Eris and Sedna, we have Orcus and Haumea and Makemake. Haumea actually has 2 moons. Quaoar has a small moon. Orcus has a small moon. Some of the scale info is out of date. Obviously, these are all just drawings. We don't know what these things look like because they're extremely far away. They just show up as the tiniest speck in our most powerful telescope photos. Here's a more recent one that includes Eris's moon, which we've named Dysnomia, Salacia, 2002 MS4. Some of them we don't bother giving them cool sounding mythological names. And at this point, we know of dozens of objects. So here's some familiar objects. Mercury, Neptune's moon Triton, Pluto, and Charon. Notice the Triton is actually a little bit bigger than Pluto. Eris, which we know is a little bit bigger than Pluto. And then all of these other, oops, I thought that was going to move. Oh, I thought this was animated. It's not. All of these other objects out there in the Kuiper Belt that we've identified, we've measured their orbits, we know how far away from the sun they are. And unless we want them all to be planets, we have to draw a line somewhere. And the line we draw is right here at Pluto, and saying that, all right, anything smaller than Pluto orbiting out in the Kuiper Belt is a dwarf planet. Pluto's a dwarf planet. It's not a planet anymore. It's not a meaningful distinction. It's just a vocabulary word. By the way, that means that the largest asteroid, which is an asteroid called Ceres, was actually promoted from an asteroid to a dwarf planet because it is big enough to be round and it orbits in a nice orbit of its own in the asteroid belt. And if you feel bad for Pluto for being demoted from a planet to a dwarf planet, you can feel good for Ceres for being promoted from an asteroid to a dwarf planet. So these definitions might change, but we're really guarding against planet overload when we discover objects out in the Kuiper Belt that are large enough to rival Pluto, to be the 10th, 11th, 12th, 40th, 50th planet. Many astronomers believe that if we go further out in the Kuiper Belt, we'll find objects as big as Mercury, objects maybe even as big as Mars out in the Kuiper Belt. This is a graph of objects in the Kuiper Belt. Well, objects in the outer solar system. Some things to notice about this graph. The size of the dot is roughly proportional to the size of the object. The horizontal axis is the distance from the sun in AU. So a little less than 10 AUs is where Saturn is, a little less than 20 is where Uranus is, around 30 is where Neptune is. Pluto goes from 30 out to 40 and then out to 50. And we can see that in the inner solar system, we have Saturn, Uranus, and well, the outer part of the solar system, we have Saturn, Uranus, and Neptune. And the centaurs are just asteroids. It's just a collective name for groups of asteroids that orbit between the orbits of Saturn and Neptune. This vertical axis, this I in degrees, is the angle that the orbit is inclined from the plane of the solar system. So remember I said the solar system was pretty much flat. All the planets move in the same plane. Well, some asteroids and dwarf planets have orbits that are tilted relative to that. So that's what that I is. I think the I is standing for inclination. And we can see that it's pretty sparse through here. It's pretty sparse through here. There's Pluto at about 40 AU. And then there are all these objects that orbit kind of in the same orbit as Pluto. In fact, we've given a collective name to these Pluto distance Kuiper Belt objects. We call them Plutinos, little Plutos. And then we reach the main part of the Kuiper Belt where Makemake and Haumea and some of these named objects are. And this real increase in density at around 45 AU. So now does this one scroll? This one scrolls. And then there are objects kind of the outer edge of the Kuiper Belt, and that's where we find, for example, Eris, which is not quite twice as far away, but more than half again as far away as Pluto on the outer edge of the solar system, and some of these other objects that orbit in the outer edge of the Kuiper Belt. So what we can see from this is that the solar system doesn't have a hard edge. It's got the inner part of the solar system where the big objects orbit around the sun. It's got this kind of fairly dense donut of leftover junk orbiting around the sun, things from the size of cinder block up to things the size of Pluto. And then it just kind of gradually dwindles off with the occasional large object out here. And like I said, we might find another great big Trans-Neptunian object when we launch the next generation of big space telescopes like the James Webb, which can see smaller and dimmer stuff. So we have not explored the Kuiper Belt directly. We have seen these things as tiny little points of light in our telescopes. The New Horizon spacecraft that flew past Pluto and Charon is continuing on into the Kuiper Belt and is scheduled to rendezvous with a Kuiper Belt object and take close-up photos of it at some point in the next 5 or 6 years. I'll have to check the dates on that. Why do we care about the Kuiper Belt? Why would we want to see a Kuiper Belt object up close? It's maybe worth talking about that for just a second. Let me go ahead and stop this presentation. Next week, we're going to talk about how the solar system formed. The solar system formed from a great big cloud of gas and dust. It gradually collapsed, and gravity pulled it all in, and gravity clumped everything together into a star and a bunch of planets. The further out you go into the outskirts of the solar system, the more you're looking at stuff that didn't fall into the inner solar system and participate in this clumping together. That clumped together very weakly under its gravity out there on the outer edge of the solar system. That has never been heated up by planetary interiors, that has never experienced a whole lot of heat from the sun, that has never been substantially altered by any geological processes or any planetary surface processes. When we look at material out in the Kuiper Belt, we are essentially looking at the undisturbed material that our solar system formed from. So getting a close-up look of material in the Kuiper Belt, or getting samples of material from the Kuiper Belt, or at least getting chemical measurements of the material in the Kuiper Belt, would be like getting a scoopful of the material that the solar system formed out of. So you can think of the Kuiper Belt as sort of a time capsule of the solar system's formation. So we are interested in these Kuiper Belt objects because they can tell us something, we hope, about the material that the solar system formed out of, because we're getting a look at this sort of undisturbed ice and dust and minerals that the solar system formed out of. Some of that material actually comes into the inner solar system in the form of comets, which we'll talk about next week. So the last thing we'll do next Monday in terms of talking about objects in the solar system is we'll talk about comets and asteroids just a little bit. And then on Tuesday and Wednesday, we'll talk a little bit about the formation of the solar system and how the solar system formed and what we think we understand about that process. It's all pretty new stuff. When I was your age, when I was taking college astronomy back in the late 1980s, early 1990s, we had really good theories for how the solar system formed, but they were just theories and they weren't particularly well tested because at the time we had only one example of a planetary system, ours. Since that time, through the late 90s, early 2000s, 2010s, we have discovered dozens, if not hundreds, of other planetary systems around other stars. So we now have other models for what planetary systems can look like, and that's teaching us a lot about planetary system formation. So that's what we'll talk about around the middle of next week.